Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. We have a liftoff. Liftoff on Apollo 11.
Shadow. 4 forward, drift into the right a little. 30 seconds forward, drift. Contact light. Okay, engine stop. Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground.
Okay, so we're talking geometric sequences and series in this section. We've got two main goals. To find the nth term of a geometric series, goal number 1, and goal number 2, to sum a geometric series. So to warm you up, find the next number in the sequence. 1, 2, 4, 8. What would the next one be? 16. Whoops. What would the next one be? 32. 64. What are you doing to go, recursively speaking, what are you doing to go from one term to the other? You're multiplying by 2, aren't you? Yeah. So with an arithmetic sequence, what did we do? We added a constant difference between each term to get the next term, right? Here we're multiplying by what actually turns out to be called a common ratio. So here we multiply by 2 to get the next term. So think about it. 2 times 2 is 4, or 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and so on and so forth. So this feature, this recursive feature where to generate one term in a sequence, you multiply the previous term by a number, a common number, a constant number, that feature makes it a geometric sequence. And so, by the way, we call 2 the common ratio here because if you take any term and divide by its previous term, you could figure out what that number is. This is a ratio, and it happens to be 2. So 2 is called the common ratio. It'll be the same number if you take any term, like 64 divided by 32, you'll get 2. 32 divided by 16, you'll get 2. So we call 2 the common ratio. But it's you can also think of it as the constant we multiply by to get the next term in the sequence. Just to kind of put in writing what we just said, in a geometric sequence, a term is generated by multiplying the previous term by a common ratio. We call it R in general. So, okay, recursively, can we come up with a formula, a recursive formula for kind of a generic geometric sequence? To get the nth term, if R is your common difference, what are we going to do to the n minus first term? So remember what the notation means. A subscript n minus 1 in English, that's the term or number in the sequence that comes before an, directly before an. So what do we do to an minus 1 to get an? We multiply by that common ratio R. So that's your recursive formula. But why do recursive formulas kind of stink? I mean, they're easy to comprehend. It's kind of how we think. We think first recursively usually, but why are they a pain? If I want the 100th term, what do I have to do? I have to find the first 99. That's no fun. So we like the explicit formula, even though sometimes it's harder to find, because if I want the 100th term, I plug in 100 for n, do whatever arithmetic is involved, and boom, I've got the 100th term popping out. So that's going to be our mission here in the short term, to find an explicit formula for an. And it's going to be familiar. We did this to get the explicit formula. We did a similar thing to get the recursive formula for an arithmetic sequence in the last section. So unless you're feeling argumentative, I'll bet you would agree that the first term in a sequence equals itself, right? A1 equals A1. Okay, recursively speaking, assuming the common ratio is R, in other words, the number we multiply by to get the next term is R, what would A2 be? A1 times R. What would A3 be? A2 times R, but I don't recognize a pattern, so let me put A2 in terms of A1 and just R, so that would become, that A2, I'll do that in purple, so that A2 would become A1 times R, wouldn't it? And then we still have that R right there. So those parentheses are just for emphasizing what I plugged in. I substituted A2 equals A1 times R in for A2, and I get A1 times R, which would be what? A1 times R squared, right? Okay, and then what would A4 be? Yeah, it'd be A3 times R, but what would it be in terms of A1 and R? Yeah, because we would be plugging this guy, which is A3. A1 times R squared is A3. We'd be plugging that in for A3. And then multiplying by one more R, which gives us A1 R3. I'll bet you see a pattern. What would A5 be without actually plugging in A4? What would A5 be? A1 R, no, you were right the first time. A1 R to the fourth power. So what's the pattern then? How does the exponent relate to the guy you're plugging in, which is called the index? It's always one less. Here you could think of it as R to the 1 power. It's 1 less than 2. 2 is 1 less than the index of 3. 3 is 1 less than, think of it as an input if you like. 1 less than the input of 4. 4 is 1 less than 5. So in general, dot, 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 I'll bet you can come up with the explicit formula then. What would AN equal? A1 R n minus 1. A1 times R to the n minus 1 in the exponent. And that's it. That's your explicit formula for the nth term of a geometric sequence. It only works for geometric sequences. And it's an explicit formula. That's what we like. Okay, so in this example, we want to find A5, A9, and AN, and you don't have to go in that order. But let's say we wanted A5. Would it be that hard to find A5 recursively? So you'd want to identify R first, the common ratio. So look, here's the sequence. 1, -3, 9, -27, dot, dot, dot. What would R be? Yeah, you could take the second term and divide by the first term, or any term, as long as it's not the first term, and divide by the previous term, and you'll get -3. Does everybody see how I got that? If you took the last term that's listed, -27, divided by 9, you'll get -3. You get a constant every time you divide one term by its previous number, so you know it's a geometric sequence. Okay, so if I want A5, I've got the first 4 terms. So if I want to get A5 recursively, what do I do? What do I times by -3? The term previous to A5, A4 is listed. It's -27. So take -27 times -3, and what do you get? Positive 81. And if that's all you were asked to find, you'd be done. You wouldn't need the explicit formula. You don't really need it to get A9, but it'd be kind of convenient, right? So I'm going to find AN, and then I'll find A9. I'll use the explicit formula for AN to find A9. So you don't have to find these in the order listed. So I found this one. I'm going to go to this one next and find that. Generically speaking, AN, we just developed a formula for that. It was A1 times R to the n minus 1. Write it down every time you use it. You'll memorize it. People used to memorize whole books back in the day. You guys can memorize a few formulas, right? We used to have to remember phone numbers. Some of you don't remember that. Some of you maybe never had to do that. But yeah, in your head, you'd have a whole list of your friends, your closest friends, your parents, relatives' phone numbers, and you just remembered them. I know, it sounds impossible, doesn't it? I couldn't do it anymore. I've been hobbled by my smartphone. My memory has. Anyway, if you fill this in, okay, look at the list. What's A1? What's A1? Look at the look at the sequence of numbers in green. 1. So in for A1, plug in just the number 1. So it's 1 times. Okay, we know what R is, right? I'll put that in parentheses, -3. So I guess I don't need the dot for times if I'm using parentheses. And then to the what power? Well, it's AN, so n minus 1. Or just, since multiplying by 1 doesn't do much, you could just write -3 to the n minus 1. So that's the nth term formula. So we've got 2 out of the 3 things we were asked to find. And then we also wanted A9, right? So A9, using the nth term formula, plugging in 9 for n, A9 would be negative 3 to the, yeah, well, it's 9 minus, let me go ahead and show the work. It's 9 minus 1, which gives you 8, right? Because you're plugging in the 9 right there. So you're right, though. It'd be negative 3 to the 8th power. Does anybody have a calculator handy? It can't be negative. Did I hear negative? It's an even-powered exponent, so I know it can't be negative. So when you plug it in your calculator, if you don't put parentheses around the negative 3, if you plug it in like that, it's going to take the opposite of 3 to the 8th power, which is negative. But this doesn't include the negative in the 8th power. You have to type it in like that in your calculator and on paper if you want to represent negative 3, the number negative 3 brought to the 8th power. So what did you get? 65, 61. Does everybody agree with that? Yep. Multiple confirmations. All right. Believe it or not, I don't have that one memorized.